from Friday. Mr. Zakari left me a good report. Thank you. So just to give you a heads up, turns out I have been kind of misdiagnosed with what's going on. So I actually, because none of the tests or reports that I'm getting back on my surgeries are conclusive. Nothing's matching. So I said, time out before I do any more surgery, because that's what they want to do, is a lot more surgery. I said, I'm not a pincushion. I'm going for a second opinion. So I was in New York City on Friday getting a second opinion at Sloan Kettering. So they're one of the best cancer centers we have in the country. So I went there and they get able to answer all my questions. And that's how I know things are not. Anyway, I have to go down there for some testing soon to get some more answers, but I don't know when that is. So I'll let you know, but I'm here for a while. Okay. Nothing's happening soon. It's a hurry up and wait game is what it is. Anyway, let's get back to physics. In your packet for tomorrow, you need to do pages 27 and 28. Page 27 and 28. On those two pages, there are 4 problems dealing with angled projectiles. We're going to finish that today. The unit will be done. And we're just going to do labs. And I'll give you a review assignment tomorrow. That will be due Friday. And we're going to take your test Monday next week. I don't want to give it Tuesday because I know then we're into the Thanksgiving. Some people might be leaving early, all that kind of stuff, because we only have a 2-day week next week. So I would prefer to give you the test Monday. I am not a fan of Monday tests, but kind of is what it is. All right. And that will be it. Okay, let's check your answers on page 23 and your work. I want to make sure that your work is correct as well. Okay, so the first thing you should have done with this question was made a sketch that looks something like this. Can you see it okay? Okay, so we see our parabola. We see the initial speed. We see the angle. We see the range. We see the maximum height. We see the total time in the air and the time going up. Now, from that, I taught you in the video to then break down that initial speed and the launch angle into its horizontal and vertical components. So we redraw the VI into a triangle, showing the VIX and the VIY with their arrowheads. We add them head to tail to produce that launch speed at this angle. To get the Y component of that initial speed, you're going to use AY equals A sine theta. You have to write the equation. And you plug in, so 100 meters per second times the sine of 30.0 degrees. Make sure you have that degree symbol at the end. That's equal to 50.0 meters per second with the sig figs. Now you're going to do the same thing in the X direction using AX is A cosine of theta. So you're going to take 100 meters per second and then multiply by the cosine of 30.0 degrees. That gives you 86.6 meters per second. How are we doing so far? So far, so good? Okay. After that, you should have made a table. And here's what your table looks like. I'm going to go row by row. So the first thing you're going to start with are your accelerations. In the X direction, it is 0 meters per second squared. In the Y, it's negative 9.81 meter per second squared. Then you're going to add your VIs, which you found from the trig stuff we did over here. VI in the X is 86.6 meters per second. In the Y, it's positive 50.0 meters per second. You do want that positive sign on the 50 because in the vertical direction, this projectile changes direction of motion. This is the upward path. The D's we don't know. You probably had question marks. The T's we don't know. Those are question marks. And then the VF for the top would be 86.6 meters per second in the X and 0 meters per second in the Y. How are we doing? Good so far? Okay. Now let's talk about what you were being asked to find. In part A, your unknown is dy. In part B, it's the time. And in part C, it's dx. Which part are you going to do first? Yep. And we know more in the Y direction with an A, a VI, and a VF, values changing. So we're going to use the Y direction to get it. So the equation to pick would be VF is VI plus AT. So T is VF minus VI over A The VF is 0 meters per second, so that would drop out, minus the positive 50.0 meters per second divided by negative 9.81 meter per second squared, which means the time going up is 5.10 seconds. Now, they didn't ask you for the time up. They want to know the whole time, the entire time, the hang time. So what do you do to get it? Just double it. 3 sig figs, 10.2 seconds. Now I would recommend doing part C. Get the range, dx, and I would use d as VIT plus half AT squared. The A in the x direction is 0. So that will drop out. So that means you're going to take 86.6 meters per second and multiply by 10.2 seconds, which gives you 883 meters. So far, so good? Okay. Now, to get the dy, there's actually 3 different ways you can get it, because now you know 4 things. So you have multiple equations you can pick to get it. I will show you all 3 possible ways to get this answer for d. The first way uses v bar as d over t in the vertical direction. So the d would be the v bar times the t on the way up. So I have to ask myself, what is the average of positive 50 and 0? Can you tell me what is the average of positive 50 and 0? Positive 25.0 meters per second. We multiply by just the time going up, 5.10 seconds. So if you did it that way, you would get 128 meters. Another way to do it would be using d is VIT plus half AT squared. Nothing drops out, because for the upward path, the only thing that's 0 is the VF, and VF is not in that equation. So I'm now going to plug in positive 50.0 meters per second times the time up, which is 5.10 seconds, plus half of negative 9.81 meter per second squared times 5.10 seconds, which has to get squared. Now, if you plugged in 10.2 seconds, you found the displacement from launch to landing vertically. It starts on the ground, it lands on the ground. So the vertical displacement from launch to landing is 0. So if you ever get a dy of 0, that's why you have the wrong time. You didn't use half the time. So that method gets you a height of 127 meters. The third and final way to do it would be to use VF squared is VI squared plus 2AD. So D is VF squared minus VI squared over 2A. So you would do negative of the positive 50.0 meters per second, square that, and then divide by 2 times negative 9.81 meter per second squared. If you do it this way, you also get 127 meters. Okay, any questions? Liam? Would it be what?
Well, one answer is 128 meters.
Because this method, when you work it out, it rounds up to 128. These are 127.4 something. That rounds down. So I will be looking at which way you did it to come up with the correct answer. Okay. All right, let's move on then to page 24 and 25. We just have to finish these up. You will have plenty of time to work on homework in class today. Not all, you won't get through all of it, but you'll get started on it. All right, and these are a little different. So in question number 4, it says that we have a teacher who's using this apparatus to demonstrate some of the principles of projectile motion. We have a launching mechanism which gets mounted on this trolley or a cart, and it will fire a ball directly upward with an initial velocity of 3.9 meters per second. Now in part A, I want us to find the height that the ball rises to. In part B, I want us to find the time for the ball to go to the highest point. Then in part C, we are going to push the trolley so that way it travels at a steady speed of 1.1 meters per second. And when it gets to point A, the mechanism will fire the ball vertically with an initial speed of 3.9 meters per second. I want you to calculate the distance traveled by the cart before it catches the ball. We are not going to do part D. So you can cross it out. So if I were to come up here, I'm just going to add to the sketch. When this is traveling this way and it gets here, some things are happening. We know it's moving sideways. That would be our VIX. And that would be the value given to us here. That's the horizontal speed of the cart, which is 1.1 meters per second. But we are also going to launch it upward at that velocity. This is our VI in the Y, which is 3.9 meters per second. This is obviously going to go up and out. So that way it moves outward to this point. That would be the range, the dx. When it lands there, that's t. When it goes all the way up, that would be the dy. And to get to this point, that would be the time just going up. Sketch look familiar? All right. Now, what I don't have to do in this question is make a triangle and find the VIX and the VIY because they were already given. Instead, I can go right to my chart. What do we know about the X and the Y directions of motion? We're going to start with the acceleration values. Lenore, can you tell me what the acceleration in the X direction always is? Good. Angela, can you tell me what it is in the Y direction always? Good. Now let's get the VI values in the chart. Liam, what is the VI in the X direction? Good. And Ashley, what is it in the Y direction? Yes, and since it's going up, we're going to make it positive. Remember, in the Y direction, the ball will change direction. So I want to make sure that's the positive one. Now let's talk about the VF at the top. What is the X velocity, Alexis, at the top? Well, does it change speed outward? So what would the VF have to be in this direction? There you go, 1.1. That's not going to change. It moves outward with a constant speed. Alushi, what is it going to be in the Y direction? That's right. It will stop at the top. Now, of course, the other rows we have are the D and the T rows. I don't know any of those. Those are all question marks. Okay. Let's talk about what we're looking for in part A. What is our unknown, Jacoby, in part A? So how do I write that? I don't want to spell it out. Yeah, dy. Okay, let's talk about part B. Gianni, what am I looking for in part B?
The time.
Which time?
The time to rise to the tide.
Okay, so what time is that? Look at that picture. What is that time? To go from here up to here is called the
VIY.
no. Time is what letter?
T.
So to go from here to here, what is that called? Can you see it? Yeah, it's called the time up. T up. We just want to know how much time it takes it to go up. And then in part C, Anson, what is it that we are looking for? dx. The cart is only going sideways, so that's the dx. All right, Caroline, which part of this should I tackle first? Yep. Now we have to look at which direction of motion is going to be more useful here. Based on the fact that the x velocities don't change, that's not useful. So we are left with using the y direction with these values to give us the time going up. So Dominic, can you find an equation that would work with the variables given? We have A, VI, and VF. We're looking for a T. That is correct. Now we're going to move it around to solve it for T, which means that the equation for T is VF minus VI divided by A. We're now going to do our substitution with units. The VF in this direction up to the top is 0, so I can drop that out. So I'm going to have negative of positive 3.9 meters per second divided by negative 9.81 meter per second squared. So what is the time going up? Miranda, can you tell me? How many sig figs does this have? Yeah, how many do we need? Seconds. That's right. That is the answer we were looking for. Now, when we go back to the chart to fill that in, we don't put the T up. We put the total time. Eileen, what do I do to get the total time? Yeah, let's multiply that by 2. So 0.40 times 2, Kine, would give us. That's right. That is the total time. I'm going to put that in my chart here. 0.80 seconds for both the X and the Y directions. Okay, I think we should do part C next because that's usually what we do. So Braden, can you help me out? I've got in the X direction, I have an A, I have a VI, I have a VF, I have a T. I'm looking for the D. What would you like to do? Okay. Now in the X direction, there is something that is 0. What is 0 is the acceleration, which means this half of the equation is going to drop out. So now we can do our substitution with units. We're going to take the horizontal speed of 1.1 meters per second and multiply it by the total time, it's in the air, 0.80 seconds. We're going to solve that to give us our range. Vesa, can you tell me what that is? Correct. That is the range. I'm going to take that, put that back in my chart for the range value. Now we have to come up with the distance in the Y direction. And because I have 1, 2, 3, 4 things, there's multiple equations we could select. We only have to pick one that would work. Anya, can you find an equation for us that you'd like us to use to give us that D? Okay. Now remember, when we're looking for D in the vertical direction, that is here halfway along the parabola. So because we're just looking for it to there, when we use the time, we have to use the time we found in part B, the time up, not the total. If you use the total, you're going to get a dy of 0 if you did it correctly. So let's go ahead and do our substitution with units. Nothing is going to cancel out. The VI is positive 3.9 meters per second times the time up, which is 0.40 seconds, plus 1/2 of negative 9.81 meter per second squared times the 0.40 seconds, which must get squared. We can now figure out what that maximum height is. Morgan, you have it? 0.7. That is correct. And if you want, you can put that in your chart. But you don't ever have to really go back and fill those in if you don't want to. Okay? Any questions on page 24? All right, let's go to page 25. This is our last one that we're going to do together because I think you got through 6 and 7 on Friday. Okay. With this question, we're going to cross off 2 parts. We're not going to do D or E. And that's because if I look at the trajectory of this stunt car driver in the car, notice that the parabola starts here when he takes off. He goes up, gets back to his starting height at the top of the ramp, but then he continues down below it. That is not something we can solve in this question. And parts C and D talk about it getting all the way to here, which we can't do. We don't know how to do that without quadratic formula, and we're not going to use quadratic formula. Let's just look at what we're showing you here. It tells us that the horizontal and vertical components of the velocity are being given to us. M times s to the negative 1 power is the same as a meter per second. Anything to the negative 1 power is in the denominator. So that is a meter per second. This is your VI in the x direction. This is 6.9 meters per second, and that is the VI in the y direction. So what I'm going to do is I'm going to redraw that because that doesn't look like how we normally want to do it. Remember, when we make or have our components, we want to be able to make a right triangle. And these two components have to be drawn head to tail, which means I would have VIX here. I would have VIY here. There is the VI arrow. And then there is my angle theta. So we know this side is 39 meters per second. We know this side is 6.9 meters per second. So that's just redrawing it, getting it the way we need it. In part A, it's asking you for the speed of the car at takeoff. In part B, I want the angle of the ramp. And then in part C, I want the time for it to get to its highest point. Why don't we make our chart? What do we know about the different directions? X and Y. Let's start with the acceleration. Jacoby, can you tell me what the acceleration is in the X direction, please?
0 meters per second squared.
Good. Alucci, what is it in the Y direction, please? Good. Now we'll get our VIs. Alexis, in the X direction, the VI is? Good. And what is it in the Y direction, Ashley? Yep, and we'll make that positive to show it was going up. The next row we'll add is the VF at the top. Liam, what is the VF at the top in the X direction?
39.
Yep. And Angela, what is it in the Y direction? Good. Now we don't have our D's. We don't have the T's. So we're just going to leave those all question marks. All right. What am I asking you to find in part A? Anyone know? When I say, what is the speed of the car at takeoff? What does that mean I'm asking you for? Morgan? VI. Yep. I'm looking for the VI. In part B, what are we looking for? Lenore, can you tell me what I'm looking for in part B? Theta, that's right. And then in part C, time to get to the highest point, Anya, what would that be? That'd be a time. So time up, right? To get to the highest point, it's just the time going up. We're actually going to start with part A. We're going to start with part A. I want to get the VI first from this triangle. Brayden? Very good. We're going to use Pythagorean theorem, a squared plus b squared equals c squared. Now, if you haven't already, make sure that you have this checked off on your reference table. It's not on page 6. It's on page 5. Geometry stuff. There it is. There's your Pythag. So by writing that down, you're going to start to get some partial credit. Let's go ahead and do our substitution with units. That means we have 39 meters per second squared plus the quantity 6.9 meters per second, which must get squared, to equal the VI, which we're looking for, which has to be squared in that equation. All right, I'll give you all a minute to solve it for VI. Got it? Excellent. 40 meters per second is the VI. That doesn't go in the table because it's not X and it's not Y. Now we got to come up with the theta in this triangle. What equation should we write to help us get this angle in our triangle? Remember, you do have your reference table geometry page to help you figure out how to come up with an angle when you have two sides of the triangle that you know. Who thinks they know? Kine? Yep. So, so the tangent, and I'm not going to use the letters A and B. I'm going to change them to what we call these sides using SOHCAHTOA. Yeah, or opposite over the adjacent. So now you got to solve it for theta, which I had written on my reference table. Did you do that? Did you write it on your reference table as well? Like I did right there. So that means theta is the inverse tangent of the opposite over the adjacent. Okay, so now you got to figure out when you do your substitution with units, which is the opposite side of that angle in that triangle? Which one's the opposite, Caroline? That's right, 6.9 meters per second, and the adjacent is 39 meters per second. So now you're going to go ahead and solve that. Notice the meters per second, the units will cancel out, which is good. And we're going to round to the nearest degree, which means the ones place digit needs to be significant. So what angle does this give you? Liam?
10 degrees.
And so if I want the ones place digits to the nearest degree to be significant, what do I have to put after that zero? A decimal point. There you go. 10 degrees. That's nearest degree. Okay, now back to what we usually do, finding time. Which set of givens is going to be the most useful here to get the time? The Y, that is correct. Okay, we need an equation with the A, the VI, and the VF. Who's got it? What's that equation? Liam? Good. So let's move it around for T. That's VF minus VI over A. The VF is 0. So when we go ahead and do our substitution with units, we're going to have negative of positive 6.9 meters per second all over negative 9.81 meter per second squared. And that's going to help you get the time up. Anson, do you have it?
170.
Excellent. That is correct. Okay? Feeling all right with this? Okay. So we got 10 minutes. You can use that time to work on homework unless you owe me quizzes, which there are several of you that do. I'll have you start taking those makeup quizzes now. So that way you're all set. Tomorrow's quiz, you get to use page 27 and 28 to help you do it. So make sure you're showing all your work. That way you've got something to look at, right, to help you work it through. Okay, go ahead and work on that now. Well,